Out of Pamplin, I studied business information technology, which was about as technical as a business degree can get. And then got my master's in systems engineering, which was about as soft as an engineering degree can get. So I kind of met in the middle there. Right out of school in 2002, ended up working at NSA. So I went up to Fort Meade, was doing a lot of SIGINT program project management, learning about how the intelligence community worked and how it was supporting the DoD. NSA sent me down to work at NRO. NRO leads National Reconnaissance Office, leads the government's development of reconnaissance spacecraft. It's the government's eyes and ears in space. My role there was research and development for SIGINT spacecraft. So I was looking at next generation technologies that were being used for the purposes of improving the government's ability to monitor RF coming off the planet, right? Through that role, I had to learn a lot about small satellite technology. That was sort of emerging at the time as something that was not only interesting to the government, but was becoming commercially viable. So these dual use technologies in the small sat domain became very interesting to me. And my role was primarily exploring how we could leverage commercial services. From that, I got the bug to start a company. And when I was at Virginia Tech, I started a web design company back when businesses were first figuring out what the internet was and needing their own websites. Drillfield Design was the name of the company, and we built websites for all the pizza shops here in Blacksburg. And if we had met 15 years ago, I would have told you, yeah, I'm going to start a company, but I don't know what it is. So I ended up leaving the government in 2015 to start a company called Hawkeye 360. Hawkeye 360 is an RF analytics company. They have 31 satellites in space. The primary mission for Hawkeye is detecting wireless signals coming off the planet and using 3 spacecraft at a time to trilaterate and figure out where the signal is and put dots on a map, right? And create sort of a mapping of the RF spectrum on the planet, sort of as a GeoInt product, right? You think about satellites taking pictures from space. Hawkeye is effectively creating a product where we are showing people where things are happening on the Earth, whether it's maritime domain awareness, where cell phone towers are, where push-to-talk radios are, where Iridium handsets are, right? That sort of thing. Largely the company's largely successful. They've raised a ton of money and have a ton of government customers. Ken, who gave the last presentation, talked a lot about what it means for a company to be commercial. What does it mean for a space company to be a commercial company? I think Hawkeye 360, and in a moment I'll talk about TrustPoint, are each absolutely commercial companies, venture-backed through independent venture capital firms, but have spent a lot of time working with the US government and taking a lot of, I'll say investment, but really contract dollars from the government without at its core being a defense contractor, right? So I think that's a distinction as well. What does it mean for a company to take US government funding, but still have a vision for a broader, commercially independent, commercially viable business? I left Hawkeye in 2020 as Hawkeye was developing a product around GPS interference. And when you're mapping the RF spectrum of the planet from space, one of the things you will see is interference in GPS bands. You will see transmissions from the Earth that you're really only supposed to be seeing from space down to Earth, right? And that's interference. And those are transmissions that are causing problems for people, for governments, for entities that are using GPS for normal purposes. And the result is, it can be chaos. So mapping where the interference was coming from was very valuable to the US government in particular, but also international governments. And the product Hawkeye was selling was maps and information about GPS interference. Understanding that problem existed, I left Hawkeye to start TrustPoint. And TrustPoint is effectively building a commercial alternative to GPS, or an augmentation, providing an alternative signal for GPS. And in a moment, I'll talk briefly on the history of GPS. The slides are going to look super technical, and I will talk to it at a high level. So if you want to process meaningful technical language, look at the slides instead of listening to me. I'll keep it very high level for sure. This is not intended to be a life cycle, but like TrustPoint's brought me back here as well. Maybe in the future I'll go back into government. I don't know, but the connections have all served me very well, and I'm really glad to be here and chatting with you all. The idea of GPS has been around for over 50 years. GPS developed by the Department of Defense, originally became fully operational in 1995. And there was an intentional decision along the way to make it available globally, right? This could have been a government-owned, government-operated system that was kept for military purposes only, and instead they elected to make it available broadly. And today, GPS is clearly a critical utility that we use for every aspect of life. And I'll say this sort of throughout the presentation, but I think a lot of people think of their Google Maps or Waze as their primary use of GPS. But GPS not only provides your position, but timing as well. And that timing piece is critical to aspects of life like financial transactions, the energy grid, telecommunications grids use it as a primary timing source for remote base stations. So GPS has become a essential part of life. I won't dig too much into the depths of the history here, but there are ideas around space-based positioning, navigation, and timing from the 60s, and then ultimately making their way to a few different options relative to how we were going to actually execute a space-based positioning solution. The way GPS works today is that it is a computation performed on the user equipment, right? So the user equipment you hold, whether it's your phone, your iPad, your Tesla, your DJI drone, those devices have GPS, GNSS chips, receivers that receive multiple signals from a variety of GPS satellites, right? The GPS satellite is constantly broadcasting a positioning signal that has information. I'll show you kind of what's in the message in a second. But it's one way, right? It's blasting down, and then the device is calculating where it is based on when it's receiving those signals and what it knows about where the satellites are. Okay, so it's sort of this trilateration from space, sort of the inverse of the Hawkeye 360 mission, which is looking at one signal from multiple satellites. The government looked at multiple ways to do it. They looked at ways where the signal could be transmitted from a user, up to a satellite and back. They looked at ways where the computation could be done by like a third-party ground station, which would offload a lot of the processing power, which at the time was fairly expensive. But this is where they settled, and it's actually turned out very well. Picture 3 signals, usually 4 in 3-dimensional space, coming to a single point, being received. You do some math, you figure out where you are, right? The GPS solution today sort of gives you 3-meter accuracy. Sometimes the government will say 1 to 3 meters, sometimes they'll say 3 to 7 meter. But like 7 meters is pretty big, right? So one of the things I'll talk about today is about the performance of GPS and what future applications are looking at for positioning accuracy, and how GPS satisfies those, and how it may come up a little bit short. There are 24 satellites. I think there are 30 some up right now, including spares. These satellites are 20,000 kilometers up in medium Earth orbit, in a variety of different planes, kind of spaced out as evenly as possible. Most of these satellites are launched on fairly dedicated missions, so they can go into very specific orbits to optimize the spacing of the satellites to provide global coverage. And it's not as simple as a beep or a tone coming from space, right? There's a lot of information inside the navigation message, right? And it includes an almanac, an ephemeris of where the satellites are periodically. So you receive information from space about where the satellites are, and then effectively use the contents of the navigation message to calculate your position. GPS, which is the US government owned and operated system, is not the only GNSS system up there. Okay. It was the first. It is one of a dozen owned and operated by governments, right? So the GNSS systems of today are built, owned, operated by nation states, right? GLONASS is Russia, Galileo is the European Union, BeiDou is China, right? So there's a number of systems that are serving the same purpose. Most of them are in MEO or LEO. QZSS is a really cool orbit that you can take a look at some point, but ultimately these satellites are providing similar services to the point where companies are beginning to trust multiple GNSS solutions. And by trusting at various degrees multiple solutions, you have the ability to refine and improve your positioning accuracy. Okay, so your iPhone, the Qualcomm Snapdragon chip in your iPhone is able to receive multiple signals, not just GPS anymore, right? So if GPS were to go out, and we'll talk about threats to GPS in a second, if GPS were to go out, it can switch over to another service. TrustPoint's vision is that it is wonderful that governments are owning and operating these solutions, but there needs to be a commercial alternative, right? And in order for that to exist, there has to be a business case for it. I'll talk about that as well. But success for TrustPoint is a chip in a device that is mass produced that can receive other GNSS solutions to include TrustPoint as part of their solution. Most of the solutions I showed you a second ago are operating in L-band. So just very briefly on RF spectrum. So signals can be transmitted at different frequencies, and these are very limited resources. This is there's sort of a land grab here for spectrum, because once a frequency is used for a specific purpose, it is practically unwise to use it for other purposes for interference, because of interference. Nearly all the GNSS solutions we know today operate in L-band, sort of this 1.5 gigahertz range. Now, with that in mind, TrustPoint is looking at additional spectrum that has already been allocated for this purpose, but higher frequencies. So like 5 gigahertz in C-band is where we're spending our time. That comes with some challenges, right? Particularly on the user equipment side, but it also is open field in terms of spectrum allocation, and puts us in a different category from L-band for purposes of avoiding jamming, which I'll talk about in a bit. The real challenge with GPS is that it has become so critical to every aspect of our life, right? We use it in transportation, disaster management. It is absolutely a part of safety of life applications today. And because it's part of our everyday lives, we have a need to protect it. There is no critical utility today for which, one, there isn't a backup, and number two, there isn't a premium service. So you can think about how we use GPS today and other GNSS solutions as sort of touching every aspect of life. And it's not only on the commercial side. There is a defense analog or a defense parallel for every application that we use GPS for today. So the fact is, we need GPS, and the government is very vocal about the needs for protecting it. But for the most part, it's working today. So what are the challenges? So there are a few things. Number one, for today's precision applications, it is usually sufficient, right? 3-meter level accuracy does the job. The US government spends about $1 billion a year operating the GPS constellation. But then industry spends about $30 billion a year on correction services. Okay, so these are companies that are building technology for agriculture is probably a great example. In agriculture, if you're a farmer, you can buy a device to help augment the GPS signal for the purposes of getting precision agriculture capabilities, right? If you put another way, you can't use a machine to pick grapes off of vines if you have sort of 7-meter level accuracy. You need to know what rows you're in. This is maybe a good place to point out that space-based positioning solutions aren't the end-all, be-all of positioning, navigation, and timing, right? I think autonomous vehicles are a great example. LiDAR, radar, computer vision, IMUs are all like different ways of knowing where you are relative to your environment. GNSS is different in the sense that it's providing global absolute positioning. It's telling you where you are on the Earth. LiDAR is sort of telling you what's around you, right? So that's the primary difference. So I think of GNSS as sort of the backbone of positioning, navigation, and timing, whether it's for agriculture or autonomous vehicles. So knowing where you are accurately is expensive, and it's not available to everyone, right? You don't have precision GNSS on your phone. Further, the challenges associated with jamming and spoofing have become more prevalent in the last few years. I'll show a slide in a minute that talks about sort of the impact of jamming and spoofing. Jamming is where the frequency you're using is overpowered by interfering frequency, and you effectively can't use the GPS signal. Whereas spoofing, probably a little more dangerous. It's where you're receiving a signal that is not actually the GNSS signal you expect, but you believe it is. So it's transmitted from a third party, you receive it, you believe that it is the signal that you are expecting, and you use it to calculate your position. And if a third party is controlling that spoofed GPS signal, then you might be told that you are somewhere that you are not, right? And there are real world scenarios, probably maybe slightly too a light example is that there are folks using dating apps in the Middle East, and their position is being spoofed, and they're being matched with folks in countries that they are not friendly with, right? So they're logging into a fairly innocuous app, but the fact of spoofing is affecting who they're being matched with, right? Obviously, the use cases get more severe than that, but they both can have critical impacts on infrastructure. And it's a growing threat. Certainly, global conflict has shown that jamming is taking place in areas of war. The daily economic loss can be upwards of $1 billion a day if we were absent GPS. And these are just some, I'll say highlights, but that's probably the wrong word, from the media today, showing where jamming is taking place around Ukraine, up near St. Petersburg, in the Baltic. My understanding is that ambulance drivers are required to carry paper maps now because they are being jammed and spoofed so frequently that they can't depend on the positioning of their GPS system. It's also a problem if they're being further north and close to the spoofing taking place. So as we look ahead to future applications, even if GPS works largely today, the question is, what are the trends for commercial applications that would require better precision and more resilience? So certainly mobile networks, edge computing, things that require higher data rates, require more precise timing. Anything related to autonomous vehicles, drone delivery, urban air mobility, the future of transportation, all will depend on more accurate positioning. And like I said, those same solutions will use a system of systems. They'll use LiDAR, light detection and ranging. They'll use cameras, inertial measurement units. But ultimately, the GNSS solutions are providing that absolute positioning. So in order for a commercial company to step in and say, hey, let's offer this commercially, a couple things have to happen. Number one, I don't think Ken said this explicitly in his talk, but the government is absolutely pushing toward a philosophy, and to quote the government, pushing a philosophy for buy what we can, build what we must. Buy what we can, build what we must. Which means if there's the ability for them to procure something rather than reinventing it, they're moving in that direction, particularly in the space industry. You see it for communications. I think Ken said 80% of government communications are taking place over commercial satellites. It's absolutely happening in the launch market. The Earth observation, so the intelligence side of space is seeing an influx of commercial solutions that are augmenting the exquisite government solutions. But there has to be like a business case beyond government. So there are commercial solutions for a number of space applications. Sorry, this thing's blocking my words. All right. There are a few things that are enabling commercial companies to make a business case close. And I'll talk about a few of those. But the goals of these commercial companies are to build resilient, accurate, and secure solutions. Some of the technologies that are enabling that include access to space, so the affordability of launch, right? How much does it cost to put a constellation in space? That's not only the launch cost, but the cost of the satellites themselves. Those combined with the miniaturization of technology lead to the affordability, right? Even if launch costs per kilogram go down, if you're able to launch smaller spacecraft, your price goes down even further. And generally, the approach to space, which is sort of a fail-fast approach, allows you to build and launch spacecraft in far shorter timelines than have been done historically. So the paradigm shift, as I mentioned, government to commercial, going from sort of government performance specs to service level agreements through contracts with our customers, and then rapid upgrades are all key. I mentioned moving to C-band. So C-band is it's absolutely a new way of thinking about providing space positioning. But it's something that's been talked about for a while. It's been talked about for a while, but it's just now coming to fruition. So there's been plenty of work in C-band, understanding how using additional frequencies can be used for the purposes of positioning. With Moore's law, over time, the number of transistors is going up, and it allows us to miniaturize in particular our payload. And when I talk about a payload, the satellite is sort of the house for the brains of the satellite or the mission of the satellite, which is in the payload. And then the payload is what we are building to have a special purpose system for the purpose of positioning, navigation, and timing. That miniaturization combined with the decreasing cost of launch is allowing us to affordably build a constellation. And not just TrustPoint. There are probably 24 companies that have plans for 1,000+ satellite constellations. Ours will be about 360 satellites. If I had gone to an investor 10 years ago and said I'm going to build a constellation of 360 satellites, they would have kicked me out of the room. But now it feels modest compared to some of the other plans that are being built by other companies. So once the price of the space segment and the spacecraft gets low enough, then you can have real conversations about a business case associated with a commercial service. There's a lot of talk about, I'll say, constellation diversity. What does it mean for a mission to have a variety of orbits for the purposes of having different views, distances, power levels across the planet? We intend on operating in low Earth orbit, which means we're going to be like 550 kilometers from the Earth. One of the benefits there is this is an easy place to get dropped off right now, right? I can get commercial ride share from SpaceX all day, every day, for an affordable price into these orbits. Relative to the GPS orbits of 20,000 kilometers that are more expensive and more bespoke. So at its core, our approach to GNSS, and I know I'm talking about this sort of from a branded TrustPoint perspective, but this is the general approach of the commercial companies that are looking at GNSS solutions today. People are pushing toward LEO orbits and commercial buses. The new space vision for flexible payloads includes software-defined radios that can be programmed on orbit, modified to perhaps even transmit a different signal based on where you are over the planet. The higher the frequency, the tighter your circle, and the more flexible you can be geographically to provide a different positioning signal based on the needs or the service level agreement of a different region. You got to get the cost down, you got to deploy quickly, and you got to offer something that has better accuracy and security. So these are all things we're addressing. But the question about how you make money starts with what your business model, how your business model thinks of customers. And the primary feedback that we've gotten is that GPS users want a free experience, right? They don't want a monthly bill from a commercial GNSS provider. So to make this commercial, somebody else has to pay for this capability, right? And the business model that is sort of industry standard now is that receiver manufacturers and chip manufacturers end up being the direct customer of the signal provider. So it's access to the signal, access to the technology gets built into the chips and the receivers by Qualcomm, Broadcom, U-Blox, Trimble, the folks who are building the chips already today, right? These are product lines that exist today, but they need to make modifications to be able to receive new signals. And they're doing that already by looking at the other government signals and they've started to look at how commercial GNSS gets into that same equipment. Now, those chips then go to the end users, right? They go into the devices and into the hands of the people who ultimately benefit from the improved signal. So there's sort of this three-party system where the needs of these folks have to be communicated to the receiver manufacturers so that they're incentivized to improve their systems. So that's sort of the business relationship. The customers, we've sort of talked about this in a few fronts, but the target customers include everything from agriculture to autonomous vehicles. And they're brands that you know here. These are folks who are already procuring GNSS solutions. Some of these folks have longer user equipment timeline than others, right? If I'm talking to the Army, it may take nearly a decade to make some upgrades to some of the user equipment because it's deployed or it's complicated or it's on the older side, so it's harder to modify. But your cell phone's turning over every couple of years, right? So the opportunity for new technology on the consumer side, it'll take less time to implement new receivers in user equipment than it will to deploy a constellation, but it'll be close, right? So if I can deploy a constellation in 5 years, I got to spend a better part of my next couple of years working with receiver manufacturers to build in the capability so that there's not this race condition for having a signal on orbit and having devices that can receive it. It's a big market. This comes out of my venture capital pitch deck, right? There are I think Deloitte said it's somewhere between a 250 and a $300 billion industry for navigation services. The hardware side is well known to be 50 billion. And then we're spending a lot of time with defense. So in Ken's presentation, he talked about what it means for a company to lean on the government. We are absolutely leveraging relationships with Air Force, Space Force, Navy today. We have contracts with each of them. That is about getting government buy-in, and it's about taking advantage of non-recurring engineering that the government's willing to pay for that I otherwise would have to fund myself, but I need to do anyway. I don't think of, I think of the commercial GNSS space as being a commercial play, but there's plenty of opportunity to leverage the government in the onset to use government funding to advance the capability. It doesn't mean these companies have to fall into the trap of being defense contractors, but it's certainly something to watch out for. I'm going to kind of just flip through these quickly. Europe has extensively looked at the economics of the GNSS market and commercial uses in general. After Brexit and the fact that the UK was so heavily involved in Galileo development, but ultimately it was a European Union asset. There's been a lot of assessment as to what the future is within the EU as well as the UK. The UK doesn't own and operate a GNSS solution anymore. So there's been a lot of analysis about what it means for Europe. And I'm not going to read this whole thing, but the short version is the EU says, yes, we depend on it. Yes, we want to leverage commercial solutions. And the dependence is only getting greater. So in terms of implementation of a commercial GNSS solution, I mentioned rapid development of satellite systems. So we and other companies have built free-flying spacecraft to demonstrate the technology. So over a 10-month period from contract to delivery of a spacecraft, we've put 2 spacecraft up. TrustPoint put up the first free-flying LEO PNT satellites made by a US commercial company. And we did this over a period of a year, launched on SpaceX launches, built somewhat in Regis WeWork spaces, not clean rooms, right? So we're scrappy, we're quick, and we are already looking ahead to our next spacecraft with the intent of building out a constellation over a 5 or 6 year period. So we've already launched the first 2. We're looking at building out perhaps our first fleet of operational spacecraft over the next couple of years. That's dependent on venture capital because space hardware, despite being on the affordable side, is still expensive. And over time, as a constellation builds, you can provide varying and improving GNSS services. So you can, without full global coverage, you can provide a timing correction service. You can provide a positioning correction service. Even if you're full-time, even if your long-term goal is building out a independently operating GNSS solution. Here's an example of how a constellation of 48 satellites could provide near full coverage in northern latitudes, particularly in some of the countries that I mentioned we're having challenges with jamming today. This is something I would take to the EU and say, hey, can we help you? Can you help us help you build out sort of these first satellites at a fairly affordable place on a reasonable timeline? The US government's obviously looking at this as well. There are plans for what GPS Block 3, which is the next sort of 2026 block looks like. That's 60% launched with the US government heavily focused on addressing jamming and spoofing. I went into TrustPoint thinking there would be a higher demand for positional accuracy, but jamming and spoofing is sort of where the primary concerns are, certainly with the US government today. There's a President's PNT Advisory Board that looks heavily at sort of the state of space-based PNT, and they are full of PNT experts that ultimately believe that there's vulnerability in this critical infrastructure. I won't read you all this, but one of the primary takeaways here that I did want to share is that they put together this chart comparing what's going on in the United States to what's going on in China. In general, China is putting a lot more investment into next generation PNT than the US is, putting us in a disadvantaged position. Sort of while the PNT advisory board isn't a board that has a budget or is able to take direct action, they are clearly advising that we focus on catching up a bit. It's not just on the defense side. The Department of Transportation has been extremely vocal about need for what they call complementary PNT. They are looking at ways to ensure that there's resilience in the architecture and have a plan, have a roadmap for increased testing and procurement. DOT is probably the most vocal within the US government on the civil side about the need for that infrastructure support. And then the Defense Science Board, literally about a month ago, a little more than a month ago, put together a report asking for broad adoption of new solutions to address the challenge. So at the beginning, I talked about how C-band is something that's been talked about for a while. And even back in 2007, which was 18 years ago at this point, it was assessed that sort of broadly, as happens with any kind of technology, ideas that have been abandoned, like C-band positioning, due to technical challenges, become of interest decades later. And I think that's where we are now, right? Technology has evolved, enabling sort of a new wave of GNSS solutions. I think it includes both commercial as well as business as well as technical implementation. We're taking an approach with smaller satellites, with smaller orbits and smaller waves to provide that solution. And generally, the solution we're offering is intended to prove that sort of as an extension of the dual use technologies that GNSS is a commercial play. My last bullet here about government action, I always leave that on there in case there's somebody in the audience who's able to influence government action. But we are eager to work with customers on the government and commercial side for implementation. So that's all I really wanted to cover today. ChatGPT did give me most of the graphics for today, so thank you for putting up with the funny colors and everything. But I lost my voice at a football game and I thought it was coming back, but here I am. So questions. I said I wanted to be interactive and then I rambled for 40 minutes. Yes.
Yeah, are you envisioning something like an iPhone, I don't know, 25 having a C-band receiver as well as a receiver?
Yeah, there's certainly the ability to miniaturize the front ends and the antennas, right? SERPA antennas getting fit the size of a credit card, right? Can get into these things. A lot of 6G technologies are inclusive of sort of C-band frequencies already. So some of those might be built in already in some of the user equipment we're looking at. Certainly the holy grail is mass production devices, right?
I mean, roughly how much capital, I mean, you say how much capital you need to raise before you actually, because you need to get quite a few satellites up there before you really start making money.
Yeah.
What kind of capital are you talking about?
Yeah, so I mean, let's see. We publicly say that our target is $250,000 per satellite on orbit. So that includes bus, payload. It includes a lot. Yeah. So, and I think our first ones were more than that. So that number is a target when we get to the economies of scale of ordering 100 at a time instead of one at a time, right? But I think all in, we can launch our constellation for the same price as a single GPS satellite, and then operate it for 1/100th of the cost.
Like size and mass, roughly.
Yeah, I think one of our slides talked about our payload sort of ultimately being a 2U payload. So it could be 10 centimeters by 10 centimeters by 20 centimeters. Our first generation was smaller than that, but less capable than what we want it to be ultimately. These can fly on CubeSats, microsatellites, 15-kilogram spacecraft, right? These are sort of Starlink class spacecraft.
Too low, you're not going to get. I mean, GPS satellites last for 20 years. You're not going to get it.
Yeah, so you get a 3 to 5 year design life, and that means I'm launching 100 satellites a year for replenishment. I know, right? But still, at this price point, not only do I have to put new satellites up, but I have the benefit of putting new satellites up because I can put my next generation technology on it. Right, that is the philosophy of New Space, and I've been part of all the conversations about space debris and the responsible use of space. So putting propulsion on spacecraft, ensuring they're deorbiting, like that's all sort of essential to any constellation build
So
out.
are you able to say like roughly how much you're talking, you need to raise in venture capital before you really be?
Yeah, I mean, I'll target between 75 and 100 million. Yep.
Much more than that, but-
Yeah. So, if you look at the phases we have here, I think of these in terms of phases of capability, but also phases of fundraising. We're sort of right here. If we're able to raise a 25 million Series B, 50 million Series C,
You've already raised the.
we've raised through, we're working on our Series A right now. Yeah.
Series A.
Series A, yes. And frankly, we have more in government contracts than we have in venture capital at this point. So we're fine in terms of runway, but I don't want to fall in the trap of being, beholden there. I want to have this commercial viability in hand. Sir.
Once TrustPoint is commercially viable, do you still see it potentially like piggybacking off of contracts with other companies and with the government when you're launching your new 100 satellites a year? Just adding different little capabilities.
Yeah, so I guess the question is, would we consider using our architecture for other purposes? Is that kind of what you're getting at? Yeah, I mean, so some of our philosophy, which differs from and our differentiation, which is important for any startup, right, is that we are very focused on the GPS solution, right? There are other companies who are looking at multiple services, maybe communications and GPS. In order to focus on an already challenging thing, we're not entertaining other missions really right now. Also, I'm a big believer in disaggregation, right? The satellites with fairly single purposes rather than multiple tenants on a single hosted payload. Yeah. Cool. I'll stick around. I'll be around. I'm here today and tomorrow. And thanks for sticking. Appreciate it.
Thank you so much. Awesome. So glad that you'll be around to answer any questions that we may have to follow up with that. If anyone would like to hang out in this space, we've got another exciting session after this. It is featuring Miss Pompeia Lambright, and it is growing your sales internationally. We all like making money, so it's a good place to be. Or you can go ahead and head upstairs. We're investigating the superpower of the future with Dr. Rishi Jaitley. And in the way, you can grab some snacks. If you'd like to stay, you're welcome to just hang out. If you need anything, just let me know. Also wanted to remind everyone, we're having an awesome block party tomorrow. The community is welcome. We encourage anyone who plans to attend to go ahead and RSVP for ease of access to the inside, but we're gonna have food trucks, alcohol, a band from Nashville, and a kids' court.
Great combo.
It's going to be space.
Good, our next presentation.
Yeah, no, thank you.
Yeah, as I mentioned, we're over here. Okay, I started about 30 years ago, design and manufacture DC power converters for a lot of, mostly a lot of space applications, as you have all the GPS payloads, all the satellites. But we have also a wide range of products. Both, for LEO as well as high-end, the cost, everything in between.
Yeah.
I don't know what you need any, power solutions or power converters for the kind of missions that we do.
So I can tell you that my lead for digital signal processing, my lead for our signal design, if you ask him like the one thing we need to improve, he's leading our link budget as well. He's like, we need more power. We need more, and he started with solar panels. Like he's like, we need more than what we have on our sat today. But power efficiencies for conversion, I think would be useful for him to talk to as well. Now we don't build those systems. And frankly, we don't directly procure them. Like we get them through our bus provider. We now have a US-based bus provider who's incredible. It's not Pumpkin. I can't share who it is, but I mean, let's have a chat about it because when I talk to folks who have ways to improve our bus, our provider's been super open to meeting new folks and talking through how they can improve our system.
Are you also, are you familiar with a company called CZ Mastro?
Yeah,
Okay,
yeah.
we're the original investors. in CZ.
Oh, okay,
Yeah,
alright.
yeah. Have you been to their, I mean, they do like the software defined radio.
Yeah. I have a 3D printed version of one of the CZ Mastro SDRs that
Yeah.
they sent me as a promotional thing. It's
Is that right? Oh,
Yeah,
okay.
I don't know that we've used one, I don't think we've used one.
Yes. Okay, yeah.
Yeah, we've talked to them for sure. And you guys are here?
We're over here.
All right.
Just down the road.
What's the, any ties to the university? or-
Only in that I got my PhD there about 35 years ago. Yeah, this was my VP of engineering.
Awesome,
here, so,
awesome.
Melody?
Yeah, actually, yeah.
Show, you wanna let, you have to.
And by the way, I know some of the Hawkeye 360, like